Now, some of the points you have studied at your class 2 level. So we'll just glance through on those points or topics that you have studied. And some of the topics may be new to you. So there we'll be discussing a bit detail. Now, why to study crystal structure? I have already told you in my introductory class that it is the structure of the material that makes the difference. Because of the structure, we can see the different types of materials with different properties. So we will be interested in studying the mechanical properties. So some of the structures which will be relevant for us to study is like crystal structure, grain structure, microstructure. So these are the structures that will be relevant for us, and also phase structure. So these structures will be relevant for us to understand the mechanical properties of materials. So crystal structure is important, and the arrangement of atoms within the crystal makes the difference, and it determines the mechanical property also, along with the other properties. The structure may affect the other properties like physical properties and other properties also. So the structures which are relevant to mechanical properties are crystal structure, grain structure, then you have got the other types of structures. And also, we'll have to study the crystalline defects, because defects are also responsible for different types of properties, difference in properties in materials. So that is also to be studied. And we'll study that after discussing this crystal structure and different structure of materials. So the crystal structure, some of the points that you have probably studied, like crystal systems and density calculations, packing factor calculation, that you have studied. But like points like lattice plane directions, Miller indices, linear planar densities, interplanar distance calculations, and you might have done in detail about the some basic structures like a simple cubic structure, then body centered, face centered. We'll be seeing other structures also like HCP in detail. So there are devices for material characterization which will tell you the material structure, and thereby you can know the properties of the material. So about the devices and characterization techniques, that will come later, but let us first know the basics, because you will have to know how to interpret the different geometry and the different parameters that are involved in crystal structure. Then only we will be able to interpret the outputs that we will be getting from the devices that are used in material characterization. So crystal structure, some of the points that we'll be discussing, I have not listed all the points, but some of the points I have just listed here, like crystalline and amorphous material. You know what is that. Some of the terms like space lattice, crystal, lattice points, lattice parameters, unit cell basis, behavior lattice, primitive cell, non-primitive cells, coordination numbers, these things you might be knowing, but we'll be glancing through these points. Crystal systems and the different types of crystal structures we get based on the crystal systems. Then most important is the metallic crystal structure, their density calculations, APF, atomic packing factor calculations, and ionic packing factor calculations. Lattice planes and directions, Miller indices. So it is lattice planes and direction and Miller indices. These are the points to be clearly understood, and then only you'll be able to read the outputs that you will be getting from the X-ray, let us say X-ray diffraction. That is a method by which you can know the different lattice parameters and other devices like energy dissipative analysis of X-ray, EDAX, it is called EDAX. So those are the material characterization techniques that we use to know the material structure and their properties. Of course, you can calculate the linear and planar densities, density calculations, and this will directly tell you about, it will give you some indications about the mechanical properties like elastic modulus in a particular direction or along a particular plane. Then interplanar distances will give you some idea about the structure of the material. Suppose there is a alloy, and there may be some elements mixed in the alloy, and you want to know what is the percentage of each of these elements in that particular alloy. So devices like EDAX can be used. So it will give you the percentage of different components in a mixture, in an alloy. So those are the material characterization techniques used for knowing the material structure and properties. So interplanar distance calculations can be done by XRD analysis, and there are also other devices. So we'll try to know some of the basics about the structure, because it will help us to know the property of the material, and we'll be mostly concerned about the mechanical properties. So crystalline and amorphous material, as you know, the atoms may be arranged. Basically, the material consists of the arrangement of atoms. Now, atoms can be arranged in different ways. We call the crystalline arrangement or amorphous arrangement. In crystalline arrangement, the atoms are arranged in regular fashion. There will be some regular geometry. In the case of amorphous structure, it is not so. So we can predict the physical properties like density of the material and the other properties. So we need to know the atomic radius, the crystal geometry, and atomic weight, of course, for each element we know. So we can predict some of the properties, density, and thereby, some other properties also can be predicted to some extent. So you have done to some extent this FCC structure, BCC structure. I don't know HCP whether you have done all these calculations for HCP structures or not. HCP means hexagonal closed packed structure. Now, material properties generally vary with single crystal orientation. What is the orientation of the crystal? So that will give you some indication. This orientation you can have some idea about from the study of crystal, direction, plane direction and plane direction of the planes, and the direction of certain directions and plane along which you are considering you are interested in the study or arrangement of the atoms. So this will help you to know whether the material is anisotropic or isotropic. Anisotropic means material is having different properties in different directions. So sometimes materials may be non-directional also. That means in all directions, X, Y, Z, all directions have the same properties. Say tensile strength, there may be some material where you have got the same tensile strength in X, Y, and Z directions. But there will be some materials where these are not same. So these are some of the points to be seen from the structure of the material. And we can see it actually depends on the structure. So materials and packing, how the materials are arranged, the atoms in the materials are arranged. In crystalline, obviously, there will be some regular type of structure, as you can see from here. This is just an example. And in non-crystalline materials, the structure will not be same. So there are some more diagrams. It will be very clear. So there are this type of structure also affects the properties of the material. Definitely, we will see it later. So you have got the glass structure, quartz structures. So these are some of the structures of the materials. Just I have taken to just demarcate. So crystal has the building blocks crystal is the tiny single. If it is single crystal, then it is a tiny grain, single grain, we can say, single crystal. Materials can be of single crystal, polycrystalline materials can also be there. So these we'll see later on. Now here just see, let us consider a single crystal versus polycrystal properties. Now if it is a single crystal, and let us say one unit cell we are considering, for simplicity we have taken cubic structure with body center cubic structure rather. So in body center you have with the central atom at the center and 8 atoms at the corner, and we are concerned about this unit cell only. Now let us take one important mechanical property, say elasticity, elastic modulus. Now you see the the value of E or elastic modulus in this particular direction, in this direction as shown by the arrow. If you apply the force in this direction, you are getting elastic modulus around 125 GPa, let us say. And when you are applying a force in this direction, you are getting elastic modulus 273 GPa. So from outside, you cannot see just the inside of the atom with your bare eye. So, if you just think about that, we are applying forces in two directions and we are getting two different values of elastic modulus. So material is anisotropic, obviously anisotropic. It is because you can imagine if we apply this force in the horizontal direction, in this horizontal plane along this direction, we are trying to move actually only two atoms. We are trying to move the two atoms. Force is applied on the two atoms. Whereas when you are applying the force in the diagonal direction, you are trying to move three atoms. Obviously, the force that will be required to move three atoms will be much more than this direction, force required in this direction. It just gives you some indication that how the properties, mechanical properties, may affect by the structure or atomic arrangement of the material. So this is just an elementary idea. We'll see it detail in later cases. Now, when the materials will be polycrystalline, because all the crystals are arranged in random fashions and they have got an average value in all directions, so then the material tends to be isotropic material. So when the grains are randomly oriented, the material tends to be isotropic, and we may get the property, say mechanical property, say polyiron, polycrystalline. In case of iron, let us say, where the grains are or the crystals are mixed in randomly, we may get the same value of elastic modulus in all directions. It is, let us say, 210 GPa approximately. And if the grains are oriented in a particular direction, we can do. That can be artificially done. The grains are oriented in a particular direction, and thereby we can change the properties, mechanical properties. So those are the things that is called the materials manipulation, or improving the properties of materials according to our need. Manipulation means we are changing the structure of the material to suit our need. মেটেরিয়ালের মধ্যে আমি স্ট্রাকচারস, আমি মেটেরিয়াল গ্রেনগুলোকে লম্বা করে দিলাম, কিভাবে করব সেটা এখনই বলা যাচ্ছে না, বলছি না। সাপোজ গ্রেনের স্ট্রাকচার, গ্রেনের ওরিয়েন্টেশনটা চেঞ্জ করে দিলাম, আমি আগে যেরকম ছিল পরে আমি অন্যরকম করে দিলাম। সো মেকানিক্যাল প্রপার্টিস উইল বি গেট চেঞ্জড। তো দ্যাট ক্যান বি ডান। ওইগুলো আমরা যেখানে উই হ্যাভ গট দি স্ট্রেংথেনিং অফ মেটেরিয়ালস বলে একটা টপিক আমরা পড়বো, মানে স্ট্রেংথেনিং অফ মেটেরিয়ালস মানে আমরা মেটেরিয়ালের স্ট্রেংথটা বা অন্য প্রপার্টি, how we are going to improve, that will be discussing when we'll be discussing about the material defects and property improvement. So some of the terms we need to know, and you know some of the terms that I at your class 2 level is space lattice. Space lattice means it is a three-dimensional structure where the atoms are arranged. So space lattice is a part, and crystal, when you are considering a crystal, then we are referring a single crystal. That means it is a unit cell for a lattice structure, you can say. So crystal, it is crystal. It has got a typical definition. Sometimes it is defined as the lowest energy state of a condensed phase. You know, when you are cooling the material, the liquid metals gets condensed, so phase transformation takes place from liquid to solid, and the atoms are arranged in a particular form. So if it is a metal, maybe the regular crystal structure we may get. So this is the lowest energy state of a condensed phase of atoms and molecules. Then you have got the lattice point. So in the space lattice, you will find some points where the center of the atom lies. So center of the atom can be taken as lattice points in the crystal structure. Then comes the unit cell. Unit cell is the smallest building block of the crystal structure. You will find, if you see the crystal structure, you will find that the smallest block is getting repeated in three-dimensional space. So that is called the unit cell. Then comes the basis. Basis can be an atom or a group of atoms. So an atom or a group of atoms which must be placed on each lattice point in a regular fashion to get the crystal structure is known as basis. So when you are taking basis and the lattice points, basis plus lattice points makes your crystal structure. The combination of basis and lattice point makes your crystal structure. Then we know that some one particular type of lattice is called the Buddhadeb lattice, where all the atoms or ions or molecules at the lattice points are identical. When it is not, then we call it other types of lattice structures, like non-Buddhadeb type lattice structure. Then you have got the primitive cell, non-primitive cell. So there are some classifications about this. Then we know the coordination number. In case of ionic cracking factor, it is basically the ratio, or sometimes it is called the relative. This coordination number. This definition, I think it is basically the nearest number of atoms surrounding a central atom. So we take a reference atom, and the nearest number of atoms around that central atom is called the coordination number. And this coordination number and the relative size are very much related. That actually determines the geometry of the structure, crystal structure. That is very important. That we will see. Now, primitive cell is that cell that contains the one lattice point only at the corners. That means lattice points will be at the corners only. But sometimes there will be some structures where the lattice points may be not at the corner, but also there can be at the center of the edge, or it may be at the center of one surface of the cube. So at that point it will be called non-primitive cells. So these are some of the points. Just you can glance through your textbooks, any textbook you can take. So we have got the crystal systems. We have got the 7 crystal systems, to create all possible lattice structures. And according to the device, 14 standard unit cells can describe all possible lattice networks. Now, point is that nowadays, the scientists, material scientists, are trying to artificially produce different types of crystal structures known as artificial structures, which are more than these 14 types of structures. Those are called the super lattices. So there are some artificial materials that can also be there, which may not be like this. So those are complicated structures. Like when you are talking about the materials, superconducting materials, superconducting materials conducting below at low temperatures. The structure of those materials are complicated, not like this standard, 14 types of unit cells. And those superconductors are much more complicated, and more number of elements are, arranged. Atoms are arranged within the crystal structure. So those are called the super lattices. So those are the advanced study of materials. Let us first study the elementary parts. Then, if time permits, probably it will not be possible here. Those who will be interested to study material science, to develop some new type of materials, maybe they will be studying. So these are known to you: 7 crystal systems: triclinic, monoclinic, orthorhombic, tetragonal, cubic, hexagonal, rhombohedral. Now, under each of these, you have got the different numbers of crystal structure. Like under cubic, you have got, say, cubic, there can be 3 possibilities. So we have got simple cubic, body centered, face centered. Then we have got monoclinic, two types. There can be 2 types. Orthorhombic, there can be 4 types. Then we have got the tetragonal, there can be 2 types. Cubic, I have already told you, 3 types. Triclinic, their possibility is only 1 type. Then trigonal, 1 type. Hexagonal, 1 type. So if you combine all these 7 systems with different types of possible structures, we get the 14 basic types of device lattices. So here are, this slide shows you some examples of the different structures with the with their different geometry, their different lattice parameters. Here, A, B, C, alpha, beta, gamma, known as lattice parameters. A, B, C is the length in X, Y, Z directions, and alpha, beta, gamma, from the 3-dimensional geometry. So here shows the geometry of some of the structures. So these are known to you. I'm just glancing through this. Now, unit cell, cubic unit cell, simple, body center, face center, tetragonal, the tetragonal, we have got the simple and body centered. Then we have got the orthorhombic, 4 different types. It can be simple, base centered, face centered, body centered. Then rhombohedral geometry is shown. Hexagonal, monoclinic, a bit complicated. It can be simple or base centered. Then triclinic, and the hexagonal will be sliding. Others will not be studying, because most of these metallic crystal structure, you will find that either it is your simple cubic form or hexagonal. This will actually cover most of the metal. But if you want to study the other types of structure, other types of crystal structures will also be required, but we have some time limitations. So here is the structures of all 14 different types of device lattice structures, all 14. Now, metallic crystal structure density and APF calculations, these are the repetitions to you. So what I will do, I will just quickly glance through on this. If I send the slides, you can study yourself. So we will not give more time here. So metallic crystal structure, just see here, these are known to you. BCC structure, body centered, how to calculate the there some two important parameter, that is the atomic packing factor and the density given the lattice geometry. You can do that. So some of the points to be remembered, like what are the materials that we have, but I have not listed here the materials that have this type of structures. So how to perform all these calculations, it is there. You have done in your chemistry, I know that. Atomic packing factor calculations, what is the value, all these things. Face centered, then you have got the calculations of all this. Then comes the hexagonal closed pack structure. Hexagonal closed pack structure. Now, my point is that I want to ask you here one question. Can you tell me how many effective number of atoms are there in a HCP structure unit cell? In a HCP unit cell. Can you hear me?
Yes, sir.
Yes, sir.
My question, I am repeating. My question is, if you consider HCP
স্যার
structure,
আপনার ভয়েসটা খুব আস্তে আসছে।
আমার ম্যাক্সিমাম করা আছে। It is my maximum. So my question is, if you consider HCP structure, then tell me how many total number of atoms are there in unit cell and what is the effective number of atoms in a unit cell?
Sir, effective number should be 8. 4.
আমি দাঁড়াও, একটু সাউন্ড আসছে, আমি শুনতে পাই না, দাঁড়াও এক মিনিট। হ্যাঁ, এবার বলো।
I think, sir, effective number should be 4.
4.
Effective number of atoms. Yes, sir.
4. Okay. It is not correct. Anybody else?
6
আচ্ছা, 6 বলেছে। দেখবো আমরা কত আসছে। And what is the total number of atoms we have?
টোটাল নাম্বার অফ অ্যাটম 4
ইউনিট সেলে 4 কি করে হবে? টোটাল নাম্বার অফ, জাস্ট I am counting 14. That is also not correct.
17.
Effective বলেছি, আবার total number of atoms বলেছি. When you are asked total number of atoms, you have to count the number of atoms in the unit cell. And when I am telling effective, then you will have to see.
স্যার এখানে তো তাহলে 12টা থাকছে মোট, যে ইচ অ্যাটম বিলং করছে যে ইউনিট সেলে।
হ্যাঁ, ইউনিট সেলে কটা থাকছে? 12টা।
হ্যাঁ
17.
Let us see now. Let us see. So this is the geometry, and this has been shown in the giving different colors. So if you count the number of cells, you see, opore this upper surface, top surface, here you have got 7 atoms, and the lower surface you have got 7 atoms, and in between there are 3 atoms which are completely within the unit cell. So total number of atoms, if you count, it comes out to be 7 plus 7 plus 3. It comes out to be 17. And if you count the effective number of atoms, it will be 6. Now, if you think about how it is coming 6, I think you will be able to do it yourself. So it will come out as 6. Now, knowing this, you try to calculate, this will be your home task. You try to calculate this atomic packing factor, which comes out to be 74. And in this structure, you will find that there are 2 important parameters. One is called the A, the horizontal length, that is edge length of the hexagon, and there is this C, the vertical length or the length between the 2 planes, 2 parallel planes, hexagonal planes, that is called C. So the HCP structure is actually characterized by these two important parameters, A and C. And the point is that there is a relationship between C and A, but another point to be remembered is that for different elements having this, or the metals having this type of structure, there may be some variation between the relation between C and A because of the atomic radius, because there are three different types of, there may be difference in their length in radius of the atoms, slight variations, but there is an average relationship between C and A. So once you know the relationship between C and A, you can calculate your density and atomic packing factor for this particular case of geometry. So I want you that you explore that and you try to know it, or try to find out what will be the density of the material. I can tell you some materials which are having this type of structure, like zinc, cadmium, magnesium. So from the data, if you take data of zinc, you know what is the radius of zinc atom, you know what is atomic number, you know the geometry. Now try to know what is the relationship between C and A, and then you try to calculate and try to just see whether it is coming out to be 74%, atomic packing factor is coming out to be 74% or not. You check it. And then calculate the density of zinc and see what is the actual value of, or the density of zinc, whether it is coming out to be same or not. That is your home task I am giving. Okay.
Okay, sir.
না সেটা, হ্যাঁ সেটা দিয়েই করতে হবে, কিন্তু তোমার জিওমেট্রিটা এখানে দেখে নিতে হবে ঠিকঠাক করে, এটা দিয়ে করতে হবে। তুমি এখানে জিওমেট্রিটা একটু দেখে নিতে হবে তোমার। তুমি যদি অ্যাটমিক প্যাকিং ফ্যাক্টর ক্যালকুলেট করতে চাও, দেন হোয়াট উইল বি দি ভলিউম এন্ড অল দ্যাট, ওই জিনিসগুলো তাহলে ইফেক্টিভ ভলিউম কত আসছে ওইগুলো দিয়েই করতে হবে। ডেটাগুলোকে তোমাকে একটু কালেক্ট করে নিতে হবে মেটেরিয়াল সায়েন্সের, ইন এনি বুক অফ মেটেরিয়াল সায়েন্স ইউ উইল গেট অল দি ডেটা। এটা একটা এক্সারসাইজ হিসেবে তোমাদের দিচ্ছি আমি, একটু করবে। ওকে, নেক্সট। এইটা একটা এক্সাম্পল, যেমন এইখানে, হ্যাঁ জিঙ্কের ক্ষেত্রে ইট কামস আউট টু বি C/A রেশিও কামস আউট টু বি 1.85, এটা এখানে দেওয়া যাচ্ছে। আচ্ছা, জিঙ্কের ক্ষেত্রে হয়ে যাচ্ছে। তোমরা অন্য মেটাল যেগুলো আছে যেমন কোবাল্ট হয়, আইডিয়াল কেসে যেটা আমরা নিই, আমি বললাম একটা অ্যাভারেজ ভ্যালু। ইন জেনারেল আমরা যদি আমাদের কাছে যদি কোনো অন্য, দেখো সে ডিফারেন্স জিঙ্কের ক্ষেত্রে তোমার 1.85 আসছে, বাট ইন জেনারেল আমরা আইডিয়াল কেসে আমরা এটাকে 1.633 করে নিই। সো ইউ টেক this value also you will get from material science data, material science book data থেকে তুমি কিন্তু পাবে যদি you want to calculate accurately. So this data you can get for a particular material, and if you want to calculate, you can calculate and check whether the density of zinc that we are getting theoretically by calculating, considering the unit cell concept, is actually the observed value that we already know what is the density of zinc. Just check it. So this says then comes out to be simple cubic structure. Simple cubic structure is very simple, so I need not to tell you. So this is a unit cell with a cube. There is no central atom, only the atoms are at the corner. So other things you can calculate. Just 1 minute, there may be some problem in my PPT. Okay, I'll have to just again open the file. So we are here. atomic factor calculation for this type of cell. You can see yourself. I will just keep over some of the examples also you'll have to know for particular type of structure. So these are the things that you have already done. I am just skipping. So this is the unit cell calculation of HCP. Some idea may be there. So this formula you know. Now here is the topic. This topic I will explain to you slightly in detail because this is new to you. I know the chemistry syllabus of class 11. So this is not covered there. Lattice planes and directions, Miller indices. Because if you see any material characterization book, you will see that these notations, Miller indices and all these are used to define the directions and planes in the results or outputs that we are getting from material characterization devices. So you have to know the significance of these notations, how the plane is indicated, how the directions are indicated, what is Miller indices and all that. So again, it is nothing but the geometry. So this is three-dimensional geometry. There are certain notations, X, Y, Z. So when everything is there in the first quadrant, all positive, then all values will be positive. And if it is not in the first quadrant, then of course some values X, Y or Z may be negative. So that is to be kept in mind. So accordingly, the notations are given. So this is a Cartesian coordinate system and we use the usual notations. So if you want to see, we have to denote the position of atoms. Let us say this is body center. This body center cubic unit cell, we are assuming in the first quadrant with this 0, 0, 0 as the origin. So we can locate the position of each of these atoms with the coordinates X, Y, Z. So this is the system we use to know the planes and directions. So obviously, if I want to locate this particular atom, it is 1, 1, 1. So this particular atom, it is 0, 1, 1. So obviously, you can denote any particular position, not only the atoms, any position in this unit cell in terms of X, Y, Z. So this idea is used here in denoting the directions and things. Now see here, direction in a unit cell. And one point is to be remembered here, when you are looking at any direction, then definitely direction is denoted by a vector. We can consider this as vector, or we give the notation arrow. We use arrow to denote the vector. So similarly, you will have 2 points. You will have 2 points, and if you connect the 2 points with proper direction, then you will get the direction vector or the direction indices. But that is to be denoted in some in some form, in some way. That is what called the Miller indices. So in cubic crystals, the directions are vector components of directions resolved along each axis, resolved to smallest integers. Meaning of this is that suppose I have decided to take a direction, then we will try to resolve that particular direction vector into X, Y, Z. And when we are getting the resolved parts, then those resolved parts may come in fraction. If it comes in fraction, then that is to be converted into smallest integer. That is the idea. So directions are the position coordinates of unit cell where the direction vector emerges from the cell surface and converted into integers. So this point is to be kept in mind. Another point is that the direction vector or the direction indices could be shown within the unit cell, not beyond the unit cell. So whenever you are going to draw the direction, the direction vector should be within the unit cell and not outside the unit cell. So whatever direction you may show, it should be within the unit cell. Another point to be noted is that sometimes you can shift your origin. You can shift your origin. Suppose in this first diagram, when your origin is somewhere here, then of course you can imagine that it is in the first quadrant. And second diagram also it is in the first quadrant, third diagram also it is in the first quadrant. But see the fourth diagram where my origin has shifted somewhere here at O. So when it is shifted, then origin is here. So X, Y, Z direction, if we take passing through this origin, or the coordinates passing through this origin, so obviously the position of the cube will be not in the first quadrant but in some other quadrant. So that is the point to be noted, and accordingly the notations are to be given. So that is why this the directions has come as negative. That is why we give a bar sign over the numbers. So the 1 bar, then 1 bar 0 comes out to be direction. So this direction from O to N is denoted by this. How these values has come, that also will be discussing. Another thing you have to remember, that is any crystal direction is denoted or kept in the third bracket. So how these values has come, that we will see. Lot of examples are there, no problem. So suppose here in the third diagram, if you see, just we are denoting a direction, let us say 1 to M, direction 1 to M. So 1 is the tail of the vector and M is the head of the vector. So vector, if you denote by the vector, so OM is the vector. Now see, if you can locate this M point and O point and take the difference, so you will get the direction, no problem. Now we are doing in different form. Let us say I take the projection of this OM vector in X direction, which comes out to be 1, and I take the projection of this OM vector in Y direction, which comes out to be half. I take the projection of this vector in Z direction, which comes to be 0. So the projections are coming out to be 1, 1, 0. So that is to be made into that. So 2, 1, 0. So that is the way we are going to find out any direction in this unit cell. So that is how we will be making the direction. Now, if it is not in the first quadrant, in some other quadrant, then appropriately you have to denote that, and you will make the direction vector, and you will have to find out the direction. So this is the steps. Vector is sometimes we may have to reposition the vector if necessary to pass through the unit cell origin. So first we will locate the origin. So we must have to take the reference, and reference will be the origin. Sometimes it is to be repositioned. Read the offline or the projections in the ABC. Sometimes it may so happen that ABC are not same. In some crystal, the value of A and B and C may not be same. So that time you'll have to appropriately convert these numbers in terms of A, B, and C. Number 3, adjust to smallest integer values, and enclose the square bracket or the third bracket with no commas. So these are some standard notations we use to denote the directions. So this is the example, 2 examples that we are taking here. So this is the procedures already explained. You can see some more examples here. Now when you have got, as I have already told you, A, B, C are different, then you'll have to convert it appropriately to get the values. So you'll have to see the projections, divide by the length of the unit cell, you will get the fractions, convert the fractions into integer numbers, you will get the direction. So some more examples are there. Any arbitrary point within the qubit cell. Suppose in this example we are taking, this is the initial point and this is the final point, and this arrow is passing through the cube, and within this cube we have got this length. So we know the position vector or the position of these 2 points. So you can know what is the vector just by subtracting the head point location minus tail point locations. You will get the values, and that is to be converted into integers. You will get the directions. So any vector within the unit cell can be found out by this method. Then planes, defining the crystallographic planes. Now Miller indices are used to define the planes, and how the reciprocal of the axial intercept of a plane cleared of fractions and common multiples. So this is the Miller indices. We will see how to find out, and the steps that we take, that is number 1, read of the intercepts of the plane with the axis in terms of ABC. If ABC are different, take reciprocals, that is important here. Take reciprocals of the intercepts, reduce to smallest integers values, enclose in parentheses, no commas. Here we use first bracket. We use first bracket to show a particular plane, and HKL is the standard notation of Miller indices for planes. And when you are denoting a family of planes, we can keep it in second bracket. So second bracket, HKL means a family of planes. There is some standard way of writing this. So we'll see that. So HKL, if in bracket, first bracket, HKL is written, then you will at once know this indicates the planes. And from here we can find out what will be the value of x, y, z, where the planes have intercepted the x, y, and z axis, if you take the reciprocal of HKL. So that's what. See this. Miller indices are used to refer the specific lattice planes of atoms. They are reciprocals of fractional intercepts with clear functions that the plane makes with the crystallographic x, y, z axis of 3 non-parallel edges of the cubic unit cell. Say for example here, if you are considering this plane in a unit cell with same unit cell of same edge length, so we will get the Miller indices of this plane as 1, 1, 1. Because if you take the intercept here, it is 1. This is for x. For x it is 1. For y it is 1. For z for it is 1. Intercept. You take the reciprocals, it will come 1, 1, 1, and you keep it in first bracket. So you will get like that. So Miller indices procedure, how to find out Miller indices. So here are some examples. Suppose I want to show this particular plane. So obviously I'll have to see what are the intercepts of this plane with the axis. So it has intercepted x at 1 and no interception. It has intercepted y and z at infinity. Y and z at infinity. So if you take the reciprocal of these intercepts, it's come out to be 1, 0, 0. So this is the notation. So Miller indices are 1, 0, 0. So h equal to 1, k equal to 0, l equal to 0. So that is the Miller indices. Suppose you want to find out the Miller indices of this particular plane. It comes out to be 6, 3, 2. How? You take the intercepts. You take the intercepts. Take the reciprocals. Convert it into smallest integers. You will get the Miller indices. So that is the way we will be doing. So some more examples are there. You can see yourself. It is quite simple. So these two simple topics we have done. Some more examples are there. Here are some more examples you can see. So family of planes, sometimes you see these planes which are passing through the surface, fixed surface of a cube. All these planes can be denoted by this, say 1 0 0. It is standard notations kept in second bracket will indicate that it is denoting all the surfaces of a cube. So this is the notation of family of planes. Next we have, okay. So now planes and direction of hexagonal unit cell, it is slightly different. We use Miller-Device indices, MB indices, combined Miller and Device indices to find out the planes and directions, and we use 4 indices. So this part today we do not have time. I have another class after this, so we will continue from this point in the next class. So I am stopping here today. 38%, 37% are there. Sandeep, you send me the attendance of these people.
Yes.
Sandeep, can you hear me?
Yes, sir. Yes, sir.
Okay, so 38 people are here. So today we are stopping here.
Thank you, sir.
ইয়েতে দেখেছো, নেটে দেখেছো, কিছু পেয়েছো? কালকে আমাকে ফোন করেছিলে, তো ওটা দেখেছো, কিছু পেয়েছো? ও কেন why? That point has been taken based on some experimental observations. Material experimental observation থেকে দেখা গেছে যে yield point আমি কোথায় নেব, কোথায় বের করব? Yield point, when the materials are getting yielded fast, plastic transformation is started. এটা on an average যেটা দেখা গেছে, when if I take the stress diagram, linear diagram, তার থেকে যখন আমার yieldingটা স্টার্ট হচ্ছে, that point is around at your 0.2% strain. এটা কিন্তু based on some experimental observations. ওই জন্য ওটাকে স্ট্যান্ডার্ড 2% স্ট্রেনে আমি yield পয়েন্টটা পাই, and that is called the true strain. অরিজিনাল ফ্র্যাকচার পর কিটা কম হবে? না, সেটা হবে, তাও হতে পারে, সেটা ডিপেন্ড করবে মেটেরিয়ালের উপর। স্ট্রেস স্ট্রেন কার্ভ একটা মেটেরিয়াল, দেখো ওর মধ্যে কমপ্লেক্স স্ট্রাকচার আছে, তো হাজার রকমের মেটেরিয়াল আছে। দিস ক্যান অনলি বি ফাউন্ড আউট বাই অ্যাকচুয়াল এক্সপেরিমেন্ট। স্ট্রেস স্ট্রেন ডায়াগ্রামটা কিরকম আসছে, তার থেকে আমি তোমার ফ্র্যাকচার পয়েন্ট স্ট্রেস কত হবে, এল পয়েন্ট কত হবে, আলটিমেট টেনসাইল স্ট্রেন্থ কত হবে, সেইগুলো আমি বের করতে পারবো। অনেক রকমের মেটেরিয়াল আছে না, তো কিছু কিছু মেটেরিয়াল ক্ষেত্রে ইউ উইল ফাইন্ড দ্যাট সে একটা তুমি একটু ধরো ব্রিটল, তার সঙ্গে একটু ডাক্টিলিটি আছে, এরকম মেটেরিয়াল নিচ্ছ, তাহলে এই মেটেরিয়ালটা যেখানে ফেল করছে ওর কিন্তু ফেলিওর স্ট্রেসটা কিন্তু একটু হায়ার দিকে থাকবে দ্যান ইওর ইল পয়েন্ট, একটু হায়ার। হ্যাঁ হ্যাঁ, এবার তুমি যদি একটু ডাক্টাইল মেটেরিয়াল লাইক মাইল্ড স্টিল বা ওই ধরনের কিছু মেটেরিয়াল নাও, তাহলে দেখা যাবে তোমার আলটিমেট টেনসাইল স্ট্রেংথ ইজ স্লাইটলি হায়ার কম্পেয়ার টু ইওর ফ্র্যাকচার স্ট্রেংথ। তো এরকম কিছু তুমি পেতেই পারো, কেন কি এটা এক একটা মেটেরিয়ালের এক এক রকমের তার ক্যারেক্টারিস্টিক। সেই ডিফারেন্স তোমাকে যদি এক্স্যাক্টলি দেখতে হয়, তাহলে ইউ হ্যাভ টু পারফর্ম এ গুড এক্সপেরিমেন্ট, দ্যাট অনলি ইট ক্যান বি ফাউন্ড আউট বাই এক্সপেরিমেন্টেশন। ঠিক আছে, স্টপ করলাম, ওকে।